Here we're going to look at a classic find the closed form of an interesting finite sum problem. So the finite sum in question goes like this. So it's 1 times 1 factorial plus 2 times 2 factorial plus 3 times 3 factorial plus 4 times 4 factorial all the way up to n times n factorial. And so obviously there's some like standard way to do that. And the standard way to do this would be by the principle of mathematical induction. So maybe we would look at the first couple of cases, come up with a guess, and then use that guess to prove the general form by induction. So today's method is a little bit different than a straightforward application of the principle of mathematical induction, although induction is still hidden in there somewhere if you look. In fact, we're going to take inspiration from calculus. And in particular, we're going to take inspiration from the following fact. So if f prime of x equals g prime of x for all x in the real numbers, so in other words, the derivative of f is always equal to the derivative of g, then that means that f and g differ by a constant. So in other words, we can say that f of x equals g of x plus some fixed number c, where c is a real number. So this follows from the fact that if you take the derivative of a constant, you get 0. So notice if we were to subtract g of x here and take the derivative, we would end up with f prime minus g prime equals the derivative of a constant, which is equal to 0. Okay, but in order to take inspiration from this fact from calculus, we need a couple of definitions. So let's maybe get those definitions on the board right now. Okay, so now we've got a definition and the proposition that will help us prove our closed form here. And so the definition goes like this. Given a sequence a1, a2, a3, we'll call it just a sub n as n goes from 1 to infinity. The discrete derivative of a sub n is given by this delta a sub n, which is a sub n plus 1 minus a sub n. So sometimes this is also called the forward difference operator. So this is called the discrete derivative because it's some discrete version of the continuous derivative from a normal calculus class. So notice we're taking the difference of two terms that are pretty close to each other. We just can't take a limit in this case because the domain is the natural numbers or maybe the integers. Then next, the proposition that will help us finish this off goes like this. If delta a sub n equals delta b sub n for all natural numbers n, so the discrete derivative of a sequence an is equal to the discrete derivative of a sequence bn, then an equals bn plus a constant for some real number constant. So in other words, if the discrete derivatives are equal, then the sequences are equal up to one constant that is fixed for all values of n. Okay, so now that we've got this proposition on the board, maybe we'll go ahead and get rid of this and then prove the proposition. Okay, so now we're going to prove this proposition, which will help us prove a closed form for our goal sequence. And so we're going to prove this proposition by induction. That's why I pointed out earlier that there is some induction that is built in here, but proving this proposition by induction gives us a tool that we can use over and over and over again. So we've proven one thing by induction that will help us prove lots of things in the future. Okay, so let's first look at our base case. So here, let's just have our setup first. We've got two sequences a sub n and b sub n. Those go from n equal 1 to infinity. So here we're just taking the domain of these sequences to be natural numbers, although you could extend this to integers if you wanted to. So our base case will be to show that a sub 1 equals b sub 1 plus a constant. But that's actually not too hard to do because we have infinite control over our constant at this stage of the game. So notice that a sub 1 equals b sub 1 plus a sub 1 minus b sub 1. Well, that's pretty clear. We've really just added and subtracted b sub 1. So this is in fact what we'll let equal c right here, this value a1 minus b1. So let's maybe go ahead and write this as b1 plus a constant, so we're good to go here. Now let's make our induction hypothesis. In other words, we want to suppose for some k bigger than or equal to 1, we have a sub k equals b sub k plus a constant, where that's the constant that we defined up there. And now we want to consider the next case. In other words, we want to consider the a k plus 1 case. So let's do that. So consider a sub k plus 1. Notice that we can write that as delta a sub k plus a sub k. And so why is that? Well, that's because delta a sub k is equal to a sub k plus 1 minus a sub k by our definition of this forward difference operator or discrete derivative. So in fact, what we've done here is added and subtracted a sub k. We've just taken the subtraction of a sub k and wrapped it up in the a k plus 1 and the discrete derivative. Okay, fantastic. But next we can apply our induction hypothesis to this guy right here to write it as bk plus a constant. So let's do that. And we can apply our hypothesis to this forward difference operator of a sub k. So I will replace the discrete derivative of a sub k with the discrete derivative of b sub k. That's our assumption here. And then I'll replace this a sub k with b sub k plus a constant. But now next we can expand this discrete derivative of b sub k into bk plus 1 minus bk, and then have this guy cancel with this guy, and we're left with exactly what we want, which is bk plus 1 plus a constant. So if we look over here at the extreme left and right hand side, we see that we have achieved the next case via our induction hypothesis, which is exactly what we need in order to finish this proof. Okay, so let's maybe get rid of this proof, and then we'll look at a couple of values of this sequence so that maybe we can guess a closed form. Okay, so now that we've proven this proposition, we can move on to our goal. But before we really prove a closed form for our goal, we need to guess a closed form in the first place. So I've done some scratch work off the camera. So if I set a sub n equal to 1 times 1 factorial all the way up to n times n factorial, in other words, the thing that we're trying to find the closed form of, then a sub 1 is 1, a sub 2 is 5, a sub 3 is 23, a sub 4 is 119, and a sub 5 is 719. Now we want to look at these and try to see if we can see maybe an easy way to write down these numbers in some sort of nice progression. And we want to be inspired by the fact that this thing is built out of factorials. So perhaps our closed form will involve factorials. So I don't know what to say, but I think you just have to look at it for a little bit, look at some values of factorials, and then hopefully come up with a guess. And you can eventually get that this is equal to 2 factorial minus 1. Notice that 2 factorial is 2. And then here this is 3 factorial minus 1 because 3 factorial is 6. This guy right here is 4 factorial minus 1. This one is 5 factorial minus 1. And then this one is 6 factorial minus 1. Okay, so that leads us to our guess that a sub n is in fact n plus 1 factorial minus 1. Okay, so let's maybe wrap this guess up with our definition of a sub n and then prove that these two are the same using our proposition. Okay, so now that we have proven our special tool and done some experimentation to guess a closed form, we're ready to prove that closed form. But before we do that, I want to add a line to our proposition, which I'll say is homework. And that is if a1 is equal to b1, then an is equal to bn for all n. So this actually proof follows very, very quickly from the construction of the proof of this original proposition. But I'll let you guys look at it carefully if you really want to. Okay, so that means all we have to do is set the left-hand side of our goal equality equal to one sequence. I'll call that a sub n, and I'll set the right hand side of our goal equality equal to another sequence b sub n. And then all that is left to do is to show that a1 is equal to b1 and that delta AN is equal to delta BN. And then by our proposition, we will know that AN is equal to BN for all values of N. So let's just reiterate here, this purple box is what we want to show to finish it off via our proposition. So let's maybe do that. So the first thing that we need to do is prove that A1 is equal to B1, but that is pretty straightforward in this case. Notice that A1 is equal to 1 times 1 factorial, which is clearly 1, which is the same thing as 2 minus 1, which is the same thing as 1 plus 1 factorial minus 1, which is B sub 1. Okay, so these have the same initial condition, if you will. Now we'll look at their discrete derivatives to make sure they have, well, the same discrete derivative. So if they have the same discrete derivative, then they differ by a constant, but the constant they differ by, if you recall from the proof, is the difference in these two terms, but these two terms have no difference at all. Okay, so let's first of all calculate delta A sub n. So notice that's A sub n plus 1 minus A sub n. Okay, so we can expand this A sub n plus 1 out into its sum. Notice we will have the sum 1 times 1 factorial all the way up to n times n factorial plus n plus 1 times n plus 1 factorial. Now we have to subtract off the previous term. Just to reiterate, this is the A sub n plus 1 term. Now we're going to subtract off 1 times 1 factorial plus all the way up to n times n factorial. So that right there is the A sub n term. But notice the vast majority of those two terms are the same. This 1 times 1 factorial will cancel with this. All the way up to this n times n factorial will cancel with that. And we'll be left with this guy right here, which is n plus 1 times n plus 1 factorial. Now we just have to check that delta B sub n is the same thing. So let's maybe go ahead and do that now. So delta B sub n, well, B sub n is defined like this. So this is going to be n plus 2 factorial minus 1. So that is B sub n plus 1 minus n plus 1 factorial minus 1. So that is B sub n. So let's maybe just point that out really carefully. This is Bn plus 1, and then this guy right here is Bn. That's the definition of this discrete derivative. Okay, well notice that the minus 1 minus minus 1 will cancel, and we are left with n plus 2 factorial minus n plus 1 factorial. But next we can notice that n plus 2 factorial is the same thing as n plus 2 times n plus 1 factorial. And then n plus 1 factorial is the same thing as 1 times n plus 1 factorial. So that's pretty trivial, but that's actually a useful observation here. Now we can factor a n plus 1 factorial out of the right of that. That'll leave us with an n plus 1 factorial here. And then left over will be n plus 2 minus 1. So let's maybe underline those so we see where that's coming from. N plus 2 minus 1, which is just n plus 1. But notice that that is exactly what we got up here for delta A sub n. So we've proven both of the things in that purple box. But proving both of those things in the purple box tells us that AN is equal to BN, but that finishes the proof of the closed form of this object. And that's a good place to stop.